All right, so let's start the seminar. And for the first session of the seminar, it's a pleasure and an honor to have Philip Wadler as a speaker. So Philip is a professor at the University of Edinburgh, and he is an extremely prolific contributor to the programming language research. So he is one of the designers of the Haskell functional programming language. He is the one who proposed monads as a way, identified monads as a way to do effectful programming in pure functional languages. He's also done a lot of work on semantics and connections with logics. For those of you who followed my lectures last year on the Curry-Howard isomorphism, I think we studied at least 3 of his papers, including the famous Theorem for Free paper, which is a beautiful introduction to parametricity theory, and also his paper on a lambda calculus equivalent to the classical logic, the sequent calculus presentation of classical logic. And he's done also a lot of work on linear types, on gradual typing, well, so I'm not going to list all of his papers. That would take way too long. But today he's going to talk about yet another thing, which is his experience as a teacher, someone who teaches programming language foundations, and someone who found it useful to helpful to use a proof assistant, so initially Coq and then Agda in this context. And I think this is a very interesting experience that he's going to share with us. Thank you, Phil.
Okay, thank you. Let's see, so first of all, do people mind if I take a photo? It's always nice to have a memory of these occasions. There we go. Yes, say Lambda. Okay. So I want to thank Xavier for inviting me and all of you for being here. I think this must be, I wrote this textbook a couple of years ago, and I've been talking about for a bit more than a year, but this has to be the perfect venue for giving such a talk. So thank you for being the perfect audience. I wrote this book in Rio de Janeiro, and Rio de Janeiro is the perfect place to write such a book because the streets are paved with lambdas. They really are. And there's me writing the book in the living room of the flat that Fonda and I live in Rio de Janeiro, looking somewhat startled. Let's see. So I stole the title for this from an old talk by Benjamin Pierce. So this was him explaining about software foundations. So I guess most people here must be familiar with Coq, which is a proof assistant. And his idea was he'd already written one textbook on teaching types and programming languages, a very nice textbook. And then he wrote a second one, Software Foundations, which was covering the same material, but now developing all the material in Coq. And the notion is that this gives the students instant feedback. So here's some of his slides. This goes back to, only to 2009. Wow, I thought this was sort of the year 0. Okay. Right, and the idea is, if you're using a proof assistant, then this gives the students immediate feedback. You can often have students not clear on what exactly it means to have a proof. What does this notion of proof mean? So I will show you very precisely in Agda how you get feedback about what it means to have a proof. And similarly in Coq, right, either you write QED and it's happy with you, or you don't. And so this is really quite helpful for students. Of course, the students then need to learn the proof assistant, and that's a lot of additional work. And of course, you get things like syntax errors, which can sometimes be hard to track down. Like I remember once spending half an hour with a student trying to figure out why this thing wasn't working. And eventually my TA came along and looked and stared at it very closely and said, that's the wrong Unicode prime. You want a different prime character for that. and then we changed it, and then it worked. So there can be very tiny things that really hold you up for a long time. So there are drawbacks, as I'm sure you all know, to working with computers, because computers can be very picky, very fussy, and the word annoying was basically invented for computers. The other thing that he pointed out was that he thought it was a lot more work for the instructor to do everything with a proof assistant than doing a pen and paper proof. I actually found writing the textbook, it went remarkably quickly. I do not think it was 10 times harder than writing a textbook in the normal way. And in some ways it's easier, because just as the proof assistant gives the student feedback, it gives the author feedback. And so the textbook is written as a literate Agda script. And that means those bits that are written as literate Agda, I know at least parse and type check. And that basically means that there's a whole class of stupid errors. And anybody who's written anything knows you make lots of stupid errors. But there's a whole class of typos and so on that simply cannot occur in that part of the text. And so for me, as an author, that's an enormous relief. And for the people reading the textbook, that's an enormous relief, because they know that there's a certain kind of error that they don't need to worry about. I will also say that if I say something that's, so I'm supposed to go on for about an hour, and if I say something that's unclear, please do pop in with a question, and then I'll also try to leave some time for questions at the end if somebody wants to argue with me or something like that. So are there any questions yet? Not yet. Okay. So my book is called Programming Language Foundations in Agda, and as I mentioned, it's a response to Software Foundations. I think I'll just skip out of this. So both of these things live as free textbooks on the web. Right, so here's Software Foundations. You can go ahead and download that and execute it. And then here's Programming Language Foundations in Agda. Oops, don't do that, do that. There we go, sorry. And let's see. Right, the book, when I wrote it, it was me and my PhD student, Wen Kaka. Wen did all the hard work of setting up all the software that you need. Turns out there's standard software. It's all written in Ruby that lets you just do a book as a bunch of markdown files and put it up and have it execute and does the continuous integration with GitHub and so on. So Wen did all that hard work, and I did not actually know Agda when I started writing the book. So Wen taught me Agda, that was very important, and quite a number of other people taught me Agda, who are listed in the acknowledgments for the book. But in particular, I'm very lucky that James McKenna works in an office next to me, and Connor McBride works in a city next to me. And quite often I get stuck on something, I talk to Connor, and he would set me straight. So if you're writing a book about dependent programming, I strongly recommend that you have Connor as your friend. That's a huge help. And let's see, we'll go through that in a minute. But it's all here, and it can all be downloaded and executed. So for 5 years, so the way this started was it went out on the Software Foundations mailing list. Has somebody used Software Foundations? Of course, for 2 years, I'd been using my new textbook. But yeah, I'd used Software Foundations for 5 years. So I said, oh yeah, I've used it for teaching, but you probably don't want me to talk about Software Foundations because I'm doing something else now. But fortunately for me, Xavier decided otherwise. So Software Foundations is a fine textbook. I enjoyed teaching from it for 5 years. But I also felt like there was an issue, right? So it uses the Coq proof assistant. And what I discovered after 5 years is the name for Coq was chosen very well. Right? There were things about Coq that I really did not like. Let's go back here. Back here. Right, so there are the books. right? And of course, the basis for all of this stuff, I need to put this in as background, is the idea of propositions as types, which I think is anybody here, we'll do it positively. Raise your hand if you know what I mean when I say propositions as types. Okay, and raise your hand if you don't know. Okay, and raise your hand if you didn't raise your hand either of those times. I can see at least one person who hasn't raised her hand at all. Okay, so I will explain briefly because a couple of people did raise their hand, which is, right, it's always scary to say, oh, I don't know something. People will think less of me. But it's really important, right? That's probably our most important skill as academics, is to be able to say, I don't know, because that's the only way you can begin to learn. So for those of you who don't know, the idea of propositions as types is a very close correspondence between various concepts in logic, such as implication, conjunction, and disjunction, and the corresponding concepts in computation. So if you're a stark intuitionist, then you believe, what does it mean to know that A implies B? Well, what does it mean to know A? It means I've got a proof of A. Intuitionists like to say evidence of A. Right? But when they say evidence, right, they don't mean something equivocal. So like when we say evidence, we mean something that you might say put before 9 judges, and then they look at that evidence and they consider it very carefully, and they use it out to figure out something that somebody considers important, say whether the prime minister lied to the queen, something like that. It's election day today, so I'm nervous. So that's evidence. And what does it mean to know A implies B? It means you have some evidence. And what is that evidence? It's evidence that, hey, it's a function, so that's why we use an arrow. It's a function that takes evidence of A into evidence of B. So that says whenever there is a proof of A, I've got a function that will turn that into a proof of B. And therefore I know A implies B. And what is evidence for a conjunction? It's a pair of things, a product. So what two things is it a pair of? It's a pair of the evidence for A, and the evidence for B. So you've got two things in your hand. And here, it corresponds to a sum. So this means you've got either something in your hand, evidence for A, or you've got evidence for B, and you know which. Right? And that's very important that the intuitionists say that you know which. That means you do not have the law of the excluded middle. Right? So the law of the excluded middle says for any fact A, either A holds or not A holds, which seems very simple and straightforward, right? So I guess most people are familiar with logic, but if you're a bit less familiar with logic, my wife Fonda's sitting here. So here's an example. There is yogurt in the refrigerator, or there is not yogurt in the refrigerator. Right? And that seems very simple, but in fact, that got me in a lot of trouble with Fonda. I only met Fonda 3 years ago. We're sort of still on our honeymoon, and she's the love of my life. But she got angry with me last week because she said, is there yogurt in the refrigerator, or do we need to go to Tesco's? And I know the law of the excluded middle, so I didn't need to go to the refrigerator. I could just say yes. Right? But she wasn't happy with that answer. So Vonda is a strict intuitionist, which means you're not allowed to say A or B unless you know which. So intuitionists actually reject the law of the excluded middle. But it means that if you have a proof of A or B, that consists of either I know A, and here's the proof, or I know B, and here's the proof. So that's called propositions as types. Many people call it the Curry-Howard isomorphism. This is actually a drawing by Luca Cardelli that he named the Curry-Howard homeomorphism, because you can see the different symbols are morphing from the symbols we use in computation at the top to the symbols that we use for logic at the bottom. But you get this strict corresponds. By the way, false just corresponds to the empty type, the type that has no values in it. And it really has to have no values in it, right? In programming languages, we often have non-terminating recursions, and an infinite loop can be assigned any type. So an infinite loop even has the type bottom. So for a strict proof assistant, you want to throw out such programs. And so you insist that all your code terminates. So I've actually said something a little bit technical now. Are there any questions yet? All right, I'll see if I can get to the point where people have interesting questions to ask. So, anyhow, that's the idea of propositions as types. And it is near and dear to my heart. I'm going to relocate my heart so it's not under the microphone. It is near and dear to my heart. When I first saw it, it just seemed a weird, almost like a pun, right? And I didn't realize that that pun was going to become the basis for my entire research career. But that's more or less what's happened. So all the important research I've done has more or less been inspired by this idea that every good idea in computing should correspond to a good idea in logic and vice versa. So that turns out to be quite productive. And in particular, you need to understand that idea to be able to read programming language foundations in Agda. Now, that same idea underlies all the work in software foundations, but it's completely hidden. So there is a chapter that's called Propositions as Types, but it's an optional chapter. You don't have to read it. And I'll explain a little bit why that's the case and why that gets in the way. Before I move on, I should also say about the name Propositions as Types. So the ideas actually go back to the intuitionists. So some people say, you shouldn't call it the Curry-Howard isomorphism. That's not fair. You have to call it the BHK correspondence after Brouwer, Heiting, and Kolmogorov. And then some other people say, well, it's not really fair to call it Curry-Howard because at the same time Howard was doing his work, De Bruyn was doing his, which had a very similar idea. So lots of different people have seemed to have encountered this idea. And depending on which name you use, people will get mad at you for using the wrong name. So that's why I started calling it Propositions as Types. It's much safer. Fewer people get mad with you. And I mentioned that I ended up basing my entire research career on a pun. And in fact, I like puns. So of course, the title of my book has to have a pun in it somewhere. But I just had this very boring title, Programming Language Foundations in Agda. I thought, no, I can't live with that, until I realized it is a pun. Because one way you can parse this is it's about programming language foundations, which happen to be done in Agda, or, right, we're doing a lot of proofs in the book. Because of propositions as types, all of our proofs are, in fact, programs, right? Because a proposition corresponds to a type, and then a proof is a program or a term that has that type. So all of our proofs are programs. That's the whole point. And so when we're programming language foundations in Agda, all the proofs we're doing are in fact about programming of language foundations in Agda. So you could parse it either way. So I realized I thought, fine, I can have a boring title because it's actually a pun. So why did I write this book? I'd been teaching with Koch for 5 years. Why did I think Koch was well named? So the big problem with this is the same as the big advantage of Koch. So the huge advantage of Koch is that you've got proof scripts. You don't just write programs. You write a program that you execute, and that gives you a proof. That proof happens to be a program. But in fact, for most of the students, they don't need to know that correspondence. I'd like them to know that correspondence. I think it's very illuminating. But it gets hidden because you've got a proof script, which deals with things like conjunction and disjunction when we're talking about programs that you're proving properties of that are written using, instead of conjunction, disjunction, products and sums. So they learn about products and sums, and they learn about conjunction and disjunction, but because conjunction and disjunction are manipulated by proof scripts, there's a whole other set of stuff they need to learn to manipulate conjunction and disjunction, which is different from the stuff that they're using to manipulate programs. So they have to learn everything twice. And they don't see very clearly this idea of propositions as types. It's there, but it's hidden. And indeed, the thing I found my students got most confused about was they understood products and sums, because they already understood about programming, but they would get confused about how to manipulate conjunction and disjunction in proofs, because that was a whole separate set of things. So they got confused about what that separate set of things was, and I had to go and the thing that the students needed the most help with during tutorials was the proof script for manipulating conjunction and disjunction, which are called, by the way, split and destruct. So that was the biggest problem. That was the thing they got most confused by. Induction could be mysterious. So again, in a proof script, you type induct on variable, and it says, okay, here's your induction hypothesis. And most of the time, I knew why that was there, but sometimes I didn't know why that was there. It would give me an induction hypothesis. I had no idea where this came from. Have you had that problem? You're smiling.
Not that much. Well,
yeah, you're very clever, so you know.
Often too weak, but that is normal. Basically, you need to generalize.
Right. But I would get things I just didn't understand where they came from. And fortunately, again, I work with lots of clever people, so I'd go see Brian Campbell, who does lots of proofs in calc, and then half the time he'd say, oh yeah, it gave you that because of this. And then half the time he would just stare at the screen for a long time. After a while, he'd say, no, I don't know why it's giving you that either. So Xavier, I guess, always knows, but at least clever people like Brian don't always know. And I certainly didn't always know. So induction could be a bit mysterious. Again, via propositions as types, what happens with induction in Agda is it's just recursion. It's just structural recursion. So you must know that the recursion terminates, which is why Agda insists on structural recursion. Calc does the same thing. But it's just recursion, nothing else. So it's much easier to explain. There are minor things about using these, like in calc, you first define the name subst for substitution, and this just says in term n, replace every occurrence of the variable x by the term m. The more normal way for theorists to write that would be something like n with x replaced by m. This is one of the many notations for substitution that exists. By the way, there's a brilliant paper by Guy Steele that appeared in Popple a couple of years ago that cites every other Popple paper up to that time, because he's just looking at the notation people use for things like substitution. And he points out that there are about 30 different notations that people have used. This is one of the most popular. So you want to define a notation, calc lets you do that, that says when I say this, it really means this. And you can do that, but then if you read the textbook, you realize that there are various places where this one's been written and various places where this one's been written. As soon as you have two names for something, both of them end up being used. Whereas it'd be nice to just be consistent and always use one name. So that's a very minor problem. And the notation, the ability to define notations in calc is really nice. In the library, the naming conventions vary widely. And then this is the one that's, as I say, near and dear to my heart, which is propositions as types is present there, but it's hidden. Right? You can read the whole book and not notice about propositions as types. So what happens if you switch to Agda? There's no separate notion of proof scripts or tactics. And now, pairing and conjunction and function and implications and disjunction and sums are identical. They're the same thing. So instead of learning two different things, there's just one thing, and it's something the students are already familiar with. Similarly, induction is the same as recursion, so it's something the students are familiar with. There's only one name, because Agda has a very clever naming scheme, so you just put some underbars where you need them, and that's the name for this. You need more spaces, because it's very flexible in names. So pretty much the only thing that's not part of a name is a space. So you need extra spaces here for this not to just stand for a single variable name, which is a little bit inconvenient. But other than that, I find it really nice. And by and large, I could, writing in Agda, use exactly the, and Unicode, write something that looks quite close to what I would write if I was typesetting it all in LaTeX. The standard library in Agda is also not perfect, but it felt to me a little bit more consistent than Calc. Maybe that's just because Agda is younger, and the older you get, the more weird things end up in the library. I'm not sure. And then very important to me is that propositions as types is absolutely central. You need to understand that to be able to write any proofs at all. Okay. Any questions yet? Let me just check how I'm doing for time. Okay. Okay. So let me say a little bit about what I learned while writing the book. I'm actually going to sit down and do a demo for you, I think. So this thing I'm complaining about Calc is that it has proof scripts. But the proof scripts are really important, right? If you didn't have proof scripts, I don't think you could do something like proving a whole C compiler correct, or doing a proof of the four-color theorem, or of the central theorem of algebra. Right? There are certain proofs that are large and really benefit from having proof scripts. And one thing that was not clear to me at all when I started writing this was, can it even be done? Right? Because the whole book was written with proof scripts. Maybe it wouldn't work to do it in Agda because the proofs would just blow up and become too large. So I simply had, when I started, I wasn't even sure if it was possible to do it. I should also mention that when I started, my idea was I will just take Software Foundations and transliterate all the proofs from Calc to Agda, but use the same book. And I started writing the book, and I thought, actually, there are lots of things in this book I don't like. I think a good rule of thumb is that you should not write a book unless you cannot not write the book. That's probably the only use of classical logic that's going to appear in this talk. And I very quickly realized that I had to write my own book. And fortunately, I had a living room to write it in. Right, so let me just show you this. So the first question was, can I even do this? So I sat down, I picked what I thought was the most central proof, which is the proof of progress for simply type lambda calculus. And let me just show you what this looks like in various places. So I think I've got this here. So here is Calc IDE, which is pretty much what I used when teaching Software Foundations. And here's the text of the book. And here's the theorem progress. Let's see if we can. Oops. Why is that not working? Oh, I have to select. Where's progress? Here it is. Right, so then you go down to there and you can single step through the proof. And right, here's the actual content of the proof written out. And then you step through it, and I'm not going to go into detail, but you can basically, right, this proof, right, proof with eauto, intros T, th, ht, remember, so there's a lot of stuff here that you need specialized knowledge to read. But here's the thing, even if you have the specialized knowledge, you cannot read this. Right? This is not readable. Is anybody familiar with chess? Right, so a chess game is written out in chess notation, which says first the king goes to this square, and then the rook goes to this square, or what have you. But it's a list of what pieces move to what squares. And the only way you can understand that is you pull out a chessboard and you start moving the pieces around. And then you understand what it's telling you. But if you just read the chess notation, you can't understand it. It's just the same here. You cannot understand this unless you've loaded it up and you actually step through. And then you can say, right, my sub-goal right now is I'm trying to show that either there's a value t or there exists a t prime, which is a term such that t reduces to t prime, where givens are the t is a term and big T is a type, and I've got a hypothesis that says in the empty context, little t has type big T. Okay? And then you can go, so this makes sense, and then we'll take the next step, which is to just remember something, and then we take this step. And now I've got my induction hypothesis. So these are the three clauses that it needs to prove. So either a variable is a value, or there exists a term such that the variable reduces, or an application is a value, or there exists a term such that it reduces to it, and so on. So these you can read as you step through it, but this is not possible to read. In contrast, now there's one other thing I want to show you actually, which is if you actually look at the textbook Software Foundations, this is in volume 2, and the chapter is Properties of STLC. Notice that here's the proof written out in English, and then there's this little square. If you click on the little square, then you see that proof that I just took you through. But it's hidden. And the reason it's hidden, I think, is because of what I just told you, which is you can't read it on its own. The only point in looking at this is when you're actually executing in Calc IDE or something else that will take you through the steps. So it gives it to you in English, and then you've got that there. Now, what happens instead here I set it up, and then here's my proof of progress. So instead of using the built-in OR, it turns out proofs are much easier to write down if you declare special purpose data types. So here, instead of saying, so I come up with this data type progress, and there are two values of this type. Either step is a value of progress n, which works if I've got some n I can pass in, such that m reduces to n, then progress holds for m. Or it's either via a step or via done, which says, okay, I know that m is a value. So if m is a value, then progress holds for m. So this says the same thing as before. It says either you've got a value, or you've got some term n such that m steps to n. So it's saying exactly the same thing. But now you can sort of read the proof. Okay, so remember the three cases we had that came through that weren't dealt with automatically were it's a variable, it's an application. I can't remember what the third one was. Probably an if then else. So another difference is in Software Foundations for simply typed lambda calculus, you need some base type, so they use Booleans, the simplest possible base type. I use Plotkin's calculus of programmable functions. So our base type is the naturals, and then we also have recursion. So this is much more powerful. This lets you program any recursive function. Right? So this is unbounded recursion, not structural recursion, which is what Agda gives you. And so remember the first case was it might be a variable, and what this line says is it can't be a variable. So this is the construct that says it's a variable, and this is the construct in Agda that says this never happens. And the reason is we're working in the empty context. So in the empty context, no variables are allowed, because every variable you have must be declared in your context. So this is just says, well, no, obviously there are no variables because we're in the empty context. So that bit of the proof is very easy. we might have a lambda term. If we've got a lambda term, notice what I'm doing here, by the way, is I'm inducting on the derivation that this is well typed, which has the same structure as the term itself. And we've introduced all this previously. So if it's a lambda terms are values, so we're done. If it's an application, this is sort of my favorite proof. If it's an application, let's look by induction at L. So we recursively invoke L. Either it will take a step or it will be done. If it takes a step, there's a rule that says this is a congruence, so we can just take a step on the left argument. Otherwise, it's a value. So let's then look at M. And again, it takes a step or it's done. And if it takes a step, again, you can take a step in the left term. We're doing a call by value calculus. So you're only allowed to do a step if you know that the left-hand thing is a value. Oh, but that's what we just found out. So we just pass that in here. So we can know the left-hand side's a value, and we can take a step, and that's a rule called xi2. Or we're done, so that means they're both values, but then by the canonical form lemma, which was proved up above, we know that a value of function type, this must have function type here, must be a lambda term. So we know L is a lambda term, and then we can take a step by beta reduction. Oh, but that means we need to know, since it's called by value, that the argument is a value, which is what we're passing in here, because that's what we worked out just here. So each thing, whether it's a step or a value, gets used exactly once. It fits together like a jigsaw puzzle. And, right, you guys are not familiar with Agda, so that might have been a bit tricky to follow. But take my word for it, my students have no trouble following that once I've taught them a little bit of Agda. And by the way, the structure of software foundations and the structure of programming language foundations in Agda is identical. The first part teaches them enough Conq or enough Agda to get by, and then the second part says, okay, now we know that, let's start developing programming language foundations. So in my case, I teach just a lot of different variants of lambda calculus. In software foundations, they teach variants of lambda calculus, but also some simple imperative languages. I didn't do that. And notice I give the proof first. The proof is written out. You can read the proof and see its structure. That's right. So you can see how many cases there are. You can see where there are subcases. And then here's the translation of that into prose. And again, you can see, in this case, I just deal with the first three cases. And this last case is the one we went through, and you can see all the subcases. So these bullet points exactly correspond to this structure here. So my hope is that the students reading this can actually read this and use the indentations on here as a guide to understanding what's said in English here. I often think that something written out formally is actually easier to follow in English, so that having it in both can be an aid to the students. Any questions yet? Not yet. Okay, I have to say something more controversial. Right, let's go back to the... Oh, I'll show you the last thing, right? So here we are executing in Conq IDE. Let's just do the same thing. So here's the same chapter. And what we can do is from the window for Agda, pull down the load command to give the load command, or I can type Control-C, Control-L. And then when I do that, you wait a minute. Oh, it's not doing it. I know why it's not doing it. This is something new that's been introduced that I don't understand why it's there, but... Oh, no, it's okay. So let's just go back and do that again. So you click on load, or you type Control-C, Control-L, and it says it's checking. And then after a moment, this bit goes into color. And here's this little message bit at the bottom. And Right. Can you see what important message it's giving us here? Right? It's blank, which means there are no type errors, which means that the chapter has successfully compiled. So the fact that it goes into color and that this is blank, if you're actually writing the book, when that happens, you get this little adrenaline rush. Because you go, I completed my proof, it's happy now, it's not giving me any errors. So this is the most exciting thing that you get to see when working in the book, is that that window is empty and everything has gone into color. So I just love it. I actually look for the colors. Even though I'm colorblind, I can see just enough. I can see, oh, it's in color now, it's done. I get very happy. No, we don't need that one. This one. Right, so there are all of the bits of the different books which I've already shown you. So, you notice that this proof and this proof, they're about the same length. They're actually for slightly different calculi. But the point is, there's not a huge difference in length between them. And this is actually readable. So it turned out that for everything in the book, this is what happened. So it did not blow up. It was possible to write the book. That was something I didn't know when I started. So I did this. This was the first proof I did. And this was the first proof I did. And it took me 2 days because I didn't know any Agda. I could do it in a bit less now. Indeed, what my students do is they're given this proof for their final exam. They're sat down at a computer, and then they're told, here's an extension to the simply typed lambda calculus you've been given, something like add S expressions to it as a new recursive type. And then they have to extend all the definitions and the proof of progress for the, this extension to simply typed lambda calculus. And they can do that successfully within 2 hours. I'll say more about that later. So that was the first thing that I learned, is that it was possible to write the book. And I should say, when talking about the difference between having proof scripts or not, I think that as a pedagogical issue for beginning students, not having the proof scripts and having readable proofs is a huge advantage. If you want to do something like proof a C compiler correct, I'm not sure the trade-offs are the same. I expect that for there you really need proof scripts, which Agda does not have yet. So that was the first thing I learned. The second thing I learned is there are two standard ways of formulating a calculus in a dependently typed language, which John Reynolds gave the name intrinsic and extrinsic. So extrinsic is you give the type rules separately. So you do something like you'd say, okay, let's work with a very tiny calculus, one with no base types. So you've got variables, lambda terms, and applications, and that's it. So variable is just an identifier. So your construct takes an identifier and returns a term. Lambda expression has an identifier and a term, and gives you a term. And then application has 2 terms that you're applying. And then separately, you give the typing rules. So you say, if in the context gamma, somewhere you have x of type A, then the variable x has type A. If in the context gamma extended by x has type A, you have n has type B, then in gamma, lambda xn is a function from A to B. And if L is a term of type A to B, and M is a term of type A, then L applied to M is a term of type B. And notice that if you erase the terms here, these are the familiar rules of logic. So this is just modus ponens, and this is implication introduction. So these are, and this is just using a hypothesis. So again, we get to cover how these look a lot like logic. and the propositions as types idea. And anybody who's looked at lambda calculus, these will be familiar rules. And what's nice is I can write them out in Agda in a way that's quite familiar. So anyhow, the idea is first you define the syntax of terms, and then you define rules that say when a term is well typed. That's the extrinsic approach. The intrinsic approach is that your terms are indexed by a context and a type. So you're saying here is the way of forming all terms of type A, and there are three of them. It's either a variable or a lambda expression or an application. And if it's a lambda expression, its type will be A to B, but that means its body must be something with, in the context gamma extended by A, whose type is B. And for application, the body is two things, something under gamma whose type is A to B, and something under gamma whose type is A, and the whole term we formed as type is B. So now your syntax rules and your type rules are the same thing, and your types are just built in. So I always thought these two are much of a muchness. There's no huge advantage between one or the other. And then after I had completed this formulation, I was sitting down at ICFP at a table at dinner, as you do with people, and David Durai was seated next to me, and he said, oh, I have an intrinsic formulation of lambda calculus that's only, I think he said a couple of hundred lines. I said, really? I was quite surprised at how brief it was. So he sent it to me, and I decomposed it. I ended up writing the chapter of my book that does the intrinsic formulation, this formulation, and indeed, it was a lot shorter. So having done it both ways, I just looked at the lengths. So I just counted up the lines of code, omitting any examples, so the actual development. And extrinsic was 451 lines, but intrinsic was 275. And so I worked out the ratio, right? 451 over 275 is 1.6. Later, I worked out the ratio again, but I did it the other way around. I got 0.6, and I went, oh, wait a minute. They differ by 1. It's the golden ratio. So my way of summarizing this is that intrinsic is golden. And so I do extrinsic first, because that's the most familiar formulation. But then for the rest of the book, I shift to intrinsic. And this has some real advantages. I mentioned that in the final exam, the students have to actually take these definitions and modify them. So the fact that they're shorter is a big help. And in fact, you don't need to prove preservation of types if you do it intrinsically, because everything's already typed. So when you write out your typing rules, that is the proof. You couldn't write them out if they weren't well typed. So there's no separate proof to do there. And even the proof that substitution works, which is the hard part, is much shorter and more convenient. And in particular, if it turns out that if you define substitution wrong, right? It's very easy to not deal with capture of bound variables properly when you're defining substitution. And I would have students that would do that on the final exam, very rarely. They would often do it on the mock exam. And then I think I only had one student ever did it on the final exam. But the point is, you don't get any feedback if you've done the wrong definition. Whereas here, it turns out that since you are actually counting your binding structure for what is called the De Bruijn representation, if you get it wrong, it gives you a type error. So it's hard to get the definition of substitution wrong by mistake. You can't ignore capture of bound variables when writing out your definition of substitution. So that kind of problem doesn't occur anymore. I've discovered this year, I had some students that were really rather less good than the average in the past, and they got a completely wrong definition of substitution. I think they just couldn't get it to go through. So to make it go through, they, since they're working in a language where, right, you can write out the infinite loop and that has every type, they say, well, if you substitute m for x in n, the answer is an infinite loop. So that's well typed, but not correct. So you can write an incorrect definition this way, but you really have to think hard to do it. You have to decide, oh, when I substitute this, I'll give an infinite loop. let's try that one. So anyhow, it's better for the students because they get much more for free, and the development is shorter. The one shortcoming is I'd like to give them a development of a dependently typed lambda calculus in Agda. Doing that in intrinsic form is still a research issue. So I tried to do it, I got stuck. I asked Connor McBride. He got stuck. So from this, I know it's a research issue. And Connor and I are still looking at it. Connor came up with a really beautiful, well, Connor and James McKenna and some others came up with a really beautiful definition of substitution that works in this formulation, which I give in the book. And if you hadn't seen that, you wouldn't come up with it. Because it says, well, to define substitution, you first have to define just replacing variables by variables, which just seems like a special case of substitution which will fall out automatically. But no, you do that first, and that works out very neatly. Yeah?
Can I ask a question? So, less ambitiously, did you do System F, for instance? Can you do System F with impredicativity?
Very good question. Can you do System F with impredicativity? Yes, I'll say a tiny bit about that at the end. But anyhow, it's still a research issue. So I'm hoping that in another few years, we'll know how to do it dependently typed languages easily intrinsically. But we don't yet. Right now, it's hard. So that might be a reason to go back to extrinsic if I want to show a dependently typed language, which I'd like to do. OK, the last thing I want to say was about something completely obvious. So let's see. Yeah. So in this book, they mentioned that if what you'd like when you formalize something is to also get an animation of it so that you can actually go through and evaluate your terms. And they're talking about something in this paper called Big Step Semantics, which more or less is an evaluator. So they say R1s get you an evaluator for free. If you use small step, you get an evaluator for free if you use Rosu's K language, or Rosu and others, K language, or Findler and others' Radix system. So those are built-in things that give you reduction. And actually, I was consulting for a crypto firm called IOHK, and Grigori was as well. So I was looking at K, and I sort of had K envy. I thought, yeah, I want that. I want to automatically get evaluators. But I had Agda. How do I get an evaluator out? What am I going to do? So this paper says you can only do it if it's built in with like K or Redx. In software foundations, okay, a script is used to do it. So you write a special script that does evaluation for you, but I don't have scripts. And even in the Poppelmark Challenge, which was issued by Benjamin and many others 10 years ago. I think there's a 10-year retrospective this year, isn't there, at Poppel? Or is it a 20-year retrospective?
No, it's not 20 years.
10 years, okay. 10-year retrospective. So when they issued it, Challenge 2A was write down proofs of preservation in progress for System F as it happened, System F sub. And then Challenge 3 was write an animator. So something that, given a term T, finds a term T prime such that T reduces to T prime. So I thought, how am I going to do this? And I pondered it for a long time before I realized it's obvious. Has anybody cottoned on to the obvious solution yet? I've told you everything you need to know. The hint is yogurt. So why is yogurt a hint? It's because when we prove progress, the answer will either be step or done. So it will tell you, is it a value or does it take a step? And if it takes a step, when it returns step, it gives you as a part of the answer n and the actual which reduction step you take. So just executing progress does a step for you. And then you can iterate. You know that you've got preservation, so you know if you take a step to m, from m to n, and m is well-typed, then n will be well-typed. So you can take as many steps as you want. So it's a very simple piece of code that you can write up, which does this. Oh, remember I said we had, so here's the code. I won't go into it in detail. But remember I said we have structural recursion, but you might have a lambda term that's an infinite loop. So you provide one extra argument, which here is called gas. Gas is just a number. It's 0 or the successor of some other number. And that tells you how many steps to take before you stop. So this will take some number of steps and then stop. And if that's not enough, you get another larger number and on you go. This is called gas by analogy with cryptocurrencies, where you also say how many resources you can use evaluating your smart program. So that was interesting to me. So this is completely obvious. This is really well known to some people. But it's not written down anywhere that I can find. And you can find things like the Popplemark Challenge that says these are separate problems. Nowhere in the Popplemark Challenge does it say, by the way, if you've answered 2, you get for free an answer to 3. Might not be as efficient as you want, but you get an answer. That's not noticed. Yes, I should.
If you use a system based on type theory.
If you use a proof assistant and if it's based on intuitionistic rather than classical logic, that's right. But under those cases, you get it for free. And that's what this was aimed at proof assistants, most of which have that. So I think the fact that they didn't notice this means they didn't know. I wrote to them, I said, did you know? And they sort of didn't answer. They said, well, you can't assume it wasn't widely known. I'm saying, yeah, but did you know? So I didn't know. Many people didn't know. I can't find anywhere where it was published. After I wrote my paper saying I couldn't find anywhere it was published, Oleg Kiselyov pointed me to a web page where he describes this, but not a published not a published paper. So lots of people did know, and then lots of us didn't know. So I hope that by putting it in the textbook and by putting it in the paper that I wrote describing the textbook, that now everybody will know, and the obvious will really become obvious. Okay, so that's what I wanted to say about the book. But to answer your question, I also consult for a crypto firm, and we need to define a smart contract language. So it's called Plutus, and it's just a library of Haskell. But Haskell's a very complicated language. You don't want a complicated language running on your blockchain. You want very simple programs that you can validate. And you want something simple enough that it's unlikely to change a lot. So, because of propositions as types, we know there's a one-to-one correspondence between Lambda calculus and natural deduction that were invented at about the same time by Alonzo Church and Gerhard Gentzen. And then those become, when you add type polymorphism, those languages become System F and polymorphic Lambda calculus, which were, again, defined by a logician and a computer scientist within a few years of each other. So what we do on the blockchain is in Cardano, which is IOHK's crypto product, our smart contract language is just System F, except we don't want to use Church numerals, we use Scott numerals, which are a bit more efficient. So we also need recursive types, and we need recursion. In fact, recursive types at negative types implies recursion, so we just have recursive types. That's a less widely known system. But basically, the way I explain this is, how do you have a smart contract language for your blockchain that will still be good 50 years from now? Answer, use one that is 50 years old and was discovered independently by 2 different researchers. So that's what we do. And so we have a business, so here's the whole syntax. We had a business case, because it turns out in the crypto world, there are a few different firms, not just OHK, that say, right, we want to be sure that our smart contract language is right. So a couple of them have tiny smart contract languages that they've proved type sound in Coq, and then we've done the same thing in Agda for ours. So we had a business case to hire James Chapman, who's sort of the world expert on this, to formalize System F with recursive types in Agda, and this is what he did. So I sketched the first bit based on what I had in my textbook, and then he filled everything in. So that's been published recently in MPC, Mathematics of Program Construction. So James is the principal author, and then all of us at IOHK that worked at it are co-authors. So yes, it can be done. James had to work pretty hard to do it, so it's not trivial. Okay, so I wrote a paper about this. It was presented at the Brazilian Symposium on Formal Methods. I got first place. I was very pleased. So that's me in Salvador holding up my first place certificate. If you want to know more about propositions as types, there's a paper published in Communications of the ACM, December 2015. Some of you are young, so you might prefer a video. There's a video for Strange Loop covering some of the same material. And of course, all testimonials these days come from Twitter. So here's one that my colleagues found. I just proved commutativity of multiplication in Agda and got way too much serotonin out of it. Programming Language Foundations in Agda is amazing. Check it out at plfa.github.io. Thank you, Phil Wadler and Wen Kaka. I should mention that after this, one great thing about having your book on GitHub is other people can contribute. So lots of people have submitted pull requests for typos, but also Jeremy Seek has written a whole new part of the book using his very simplified approach to denotational semantics. So we now have both operational and denotational semantics in the book. So it's there. You can find it by searching for me and my co-author. You could add Jeremy now, Seek. And please send your comments and pull requests. Thank you very much.